Welcome back to Python DSA. In this video, we are doing a complete deep dive into stacks and queues, two of the most essential data structures in computer science. They're simple to describe, but they power everything from your browser's back button to BFS graph traversal to the Python call stack itself. We'll build them from scratch, understand every design decision, and cover the classic interview problems. Let's get into it. A stack is a linear data structure built on one fundamental principle, LIFO, last in, first out. The last element you push in is the first one that comes back out. The best mental model is a stack of plates. You can only add a plate to the top. You can only take a plate from the top. You have no access to anything in the middle. That constraint is the entire data structure. Think about that for a second. The stack of plates analogy is perfect because it's physically enforced. You can't pull a plate from the middle without toppling the whole stack. The same constraint applies here, and it's what makes stacks useful. 5 core operations, all in constant time. Push adds an element to the top O1. Pop removes and returns the top element, O1. Peek reads the top element without removing it, O1. Is underscore empty checks whether there's anything in the stack, O1. And size returns the element count, O1. Everything is constant time. There's no scanning, no searching, no shifting. The diagram on the right shows the model. Values 10 through 40 are stacked bottom to top. A push of 40 arrives at the top edge. A pop returns 40 from the same top edge. One end, one direction. Total order. Next, let's see the LIFO property in action with a concrete push sequence. We push 10, then 20, then 30, then 40. Each new element lands on top of the previous one. The diagrams show the state of the stack after each push. The starred element is the one just added. Pop the stack back out, and what do you get? 40, 30, 20, 10, the reverse of the insertion order. That reversal property is what makes stacks so useful for problems that need to process things backward, or that need to undo a sequence of actions. Here's a real example you interact with every time you write code, the call stack inside your CPU. When main calls foo, which calls bar, which calls baz, each function call gets pushed onto the call stack. When baz returns, it gets popped. The stack goes back to bar, then bar returns, pops, and you're back in foo. Pure LIFO, exactly as we've been describing. A callout matters. Python raises recursion error when the call stack exceeds a depth of about 1,000 frames. That default limit exists to prevent infinite recursion from consuming all available memory. It's the call stack, literally overflowing. Let's build our stack class. Python's built-in list is an excellent backing store, because append and pop at the end of a list are both O1 amortized. The constructor initializes self, underscore data as an empty list. Simple. Queries. Is underscore empty checks len equals 0. Size returns len. Peek returns underscore data -1, the last element, which is our top, but raises index error if we're empty. We also add underscore len underscore and underscore repr for clean Python idiom support. Mutators. Push call self underscore data dot append item. List append is O1 amortized. Pop call self underscore data dot pop. Popping from the end of a list is O1 exactly. The demo traces exactly what you'd expect. Push 10, 20, 30. Peek returns 30 without removing it. Pop returns 30, then 20. Length is now 1. Another pop empties the stack. A further pop raises index error, caught and printed. Every edge case handled. The key insight, we map the top of stack to the end of the Python list. This is deliberate. List.pop from the end is O1, but list.pop, 0 from the front is ON. Map your DS operations to the cheap end of whatever backing store you choose. Next, Python lists are fine for most use cases, but let's also see the linked list implementation. It gives us O1 without the occasional resize that dynamic arrays incur, and it's closer to how stacks are implemented in lower-level languages. The underscore node class uses underscore slots, underscore for memory efficiency. It suppresses the per instance underscore dict underscore, reducing memory overhead for every node. Linked stack maintains a underscore head pointer. The head of the list is the top of the stack, and an underscore size counter. Peek simply reads self underscore head.data. Push is a one-liner. Self underscore head equals underscore node. Item, self underscore head. We create a new node that points to the current head, then make it the new head. One new node, one pointer update, O1, guaranteed, no resizing ever. Pop saves self underscore head.data, advances underscore head to underscore head.next, decrements underscore size, and returns the saved value. The old node is immediately unreachable and gets garbage collected. The diagrams make the pointer mechanics visual. After pushing 10, 20, 30, head points to 30, 30 points to 20, 20 points to 10, 10 points to none. Pop returns 30, and head advances to 20. clean, O1, and no hidden allocation costs. Next, here's the first classic application, checking whether a string of brackets, parentheses, and braces is properly balanced. This is one of the most common interview problems, and it's a beautiful demonstration of why stacks exist. Click the algorithm. Walk through the string character by character. When you see an opening bracket, or push it onto the stack. When you see a closing bracket, check two things. First, is the stack empty? If so, we have a closing bracket with nothing open. Return false. Second, does the top of the stack match the expected opening bracket? If not, mismatched pair. Return false. Otherwise, pop the stack and continue. At the end, if the stack is empty, everything was matched. Return true. If the stack still has items, there are unclosed opens. Return false. Click. The match dictionary maps each closer to its expected opener, making the check a single dictionary lookup, O1. Click. The trace diagram walks through, step by step. Each opener pushes onto the growing stack. Each closer pops and verifies the match. Every match succeeds. The stack is empty at the end. True. The diagram makes it trivially clear why a stack is the right tool. Brackets must close in reverse order of how they opened. That's LIFO, exactly what a stack gives you. Next, postfix notation, also called reverse Polish notation, places operators after their operands instead of between them. So instead of writing 3 plus 4 times 5 with parentheses to handle precedence, you write 3, 4, plus 5, multiply, and precedence is implicit in the ordering. No parentheses needed. Calculators and compilers use this internally because it's trivially evaluated with a stack. Click the algorithm, scan the token list. If the token is a number, push it. If the token is an operator, pop the top two values, apply the operator, and push the result back. After processing all tokens, the one remaining value on the stack is your answer. The OPS dictionary maps each operator symbol to the corresponding lambda, clean and extensible. Click the trace for 3, 4 plus 5 asterisk. Push 3, push 4, see the plus. Population 4 and 3, push 7, push 5. See the multiply. Population 5 and 7, push 35. Stack has one value, 35. Return it. Correct. The second example, 5, 1, 2 plus 4 times plus 3, evaluates to 14. Try tracing it yourself, as practice. The elegance here, the stack handles all operator precedence automatically, by evaluating eagerly as soon as it sees an operator. No precedence rules, no parentheses parsing, just push and pop. Two more stack applications on one slide, undo/redo, and iterative DFS. The text editor class uses two stacks, one for undo history and one for redo history. When you type a character, it gets pushed to the undo stack, and the redo stack gets cleared, because a new action invalidates the redo history. When you call undo, you pop from the undo stack and push to the redo stack. When you call redo, the reverse happens. This is exactly how every text editor, graphics application, and IDE implements undo/redo. The two-stack pattern is universal. Click on the right, iterative DFS with an explicit stack. This is behaviorally identical to recursive DFS, but instead of leaning on Python's call stack, we maintain our own. Push the start node. Pop, mark visited, push unvisited neighbors in reversed order to preserve traversal order. Click on the callout is important in practice. Recursive DFS on a large graph will raise recursion error once the depth exceeds Python's limit of about 1,000. Iterative DFS with an explicit stack has no such limit. For production code dealing with large or deep graphs, always prefer the iterative version. Next. Now let's flip to queues. A queue follows FIFO, first in, first out. The first element that goes in is the first one that comes out, the exact opposite of a stack's priority. Click the intuitive model, a ticket queue at a counter. New people join at the rear of the line. People are served from the front. Nobody can jump ahead. The order of service strictly matches the order of arrival. That's FIFO. Click 5 core operations, all O1. OnQueue adds to the rear. DQ removes from the front. Peek reads the front element without removing it. Is_empty checks for emptiness. Size returns the count. Click the diagram shows the two-ended nature. OnQueue arrives on the right, the rear. DQ exits on the left, the front. This is fundamentally different from a stack, which has only one active end. The queue has two, and they serve opposite roles. Notice, for a queue to have O1 DQ, you need efficient removal from the front. A plain Python list doesn't give you that list.pop, 0 is ON, because it shifts every element. This is why we use collections.dq, which is a doubly linked list under the hood, giving us O1 at both ends. Let's build the queue class, backed by collections.dequay. Click the constructor initializes self, _data equals dequay. That's our backing store. Click queries, is_empty, size, and peek, all follow the same pattern as the stack. but peak reads underscore data, 0, the front element, not the end. Underscore underscore len underscore underscore, and underscore underscore repr, underscore underscore, round out the Python protocol support. Click mutators. onQ calls self, underscore data dot append, item, adds to the rear 01. deq calls self, underscore data dot pop left, removes from the front, also 01. 2 dequay operations, both constant time. Click the demo builds a queue with values 10, 20, 30. Peak returns 10, the front. deq returns 10, then 20. Length is now 1. onQ 40. The queue state is 30 at front, 40 at rear. Click the warning callout, deserves special emphasis. Never use a plain list as a queue. List.pop, 0 is on. It has to shift every element one position to the left. If you use this in BFS, on a graph with 10,000 nodes, your supposedly OV plus E algorithm becomes OV squared plus E. Use dequay. Always. For completeness, let's see the linked list implementation. This is closer to how queues are built in languages without a standard dequay. Click the underscore node class uses underscore underscore slots underscore underscore for the same memory efficiency reason as before. Click linked queue maintains both a underscore head, the front, and a underscore tail, the rear. Both pointers are essential for O1 at both ends. Head is the dequeue side. Tail is the onQ side. Click onQ creates a new node, attaches it to self. Underscore tail.next, then advances underscore tail to the new node. Edge case. If the queue was empty, the new node becomes both head and tail. Click the underscore head.data, advances underscore head to underscore head.next, and handles the edge case, where the queue just became empty. In that case, underscore tail must also be set to none, otherwise we'd have a dangling tail pointer. Click the diagrams show the before and after states. After enqueuing 10, 20, 30, head points to 10, tail dotted line points to 30. After dequeuing, head advances to 20, tail still points to 30. The structure stays consistent with 2 pointer updates. A circular queue, also called a ring buffer, is a fixed capacity queue implemented as an array with 2 integer pointers that wrap around using modular arithmetic. It's the basis for many high-performance buffers in operating systems, network drivers, and audio processing. Click the constructor takes a capacity. We allocate capacity plus 1 slots. The extra slot is needed to distinguish a full buffer from an empty one. Underscore front and underscore rear both start at 0. Is underscore empty is true when front equals rear. Is underscore full is true when rear plus 1% cap equals front. The rear pointer has wrapped back to 1 step behind the front. onQ stores the item at the rear slot, then advances rear with self underscore rear plus 1% self underscore cap. dequeue reads the front slot, clears it, advances front the same way. Click the diagram shows a CAPACITY5 buffer after enqueuing 1, 2, 3, and then dequeuing 1. The front pointer is at index 1, pointing at the value 2. The rear pointer is at index 3, the next empty slot. The used slots are 1 and 2. The dotted wraparound arrow shows that the end of the array connects back to the beginning. Click the callout says it all. Rear plus 1% capacity is the entire magic. It wraps the pointer back to 0 when it reaches the end of the array. No data is ever shifted. No memory is reallocated. The buffer reuses slots as they're freed. If the stack is the natural partner of DFS, the queue is the natural partner of breadth-first search. BFS explores a graph level by level, all vertices at distance 1, then all at distance 2, and so on. To do that, it needs to process vertices in the order it discovers them, FIFO, exactly what a queue provides. Click the implementation, mark the start node as visited, enqueue it. Enter the main loop, dequeue a node, record it, then enqueue all its unvisited neighbors, marking them as visited immediately to prevent duplicates. The visited on enqueue pattern is critical. If you wait to mark visited on dequeue, the same node can be enqueued multiple times from different neighbors, causing redundant work and potentially corrupting results. Click the demo graph has 7 nodes in a tree-like structure. BFS from node 0 visits, 0 first, then 1 and 2 at level 1, then 3, 4, 5, 6 at level 2. Output, 0, 1, 2, 3, 4, 5, 6. Click the diagram color codes the levels clearly. Red for level 0, medium blue for level 1, dark blue for level 2. BFS guarantees that when you first visit a node, you found the shortest path to it, in terms of hop count. That makes it the algorithm of choice for shortest path problems in unweighted graphs. Next, a priority queue generalizes the queue concept. Instead of serving elements in the order they were added, it always serves the element with the highest priority or lowest priority number in min-heap terms, regardless of insertion order. Think of an emergency room. Patients aren't seen in arrival order. Critical cases jump to the front regardless of when they showed up. Click Python's heap queue module implements a minute heap, a complete binary tree stored as an array, where the minimum element is always at the root, accessible in O1. We build our min priority queue class around it. The tiebreaker counter self _IDX ensures that equal priority items preserve insertion order, necessary because tuples are compared element by element, and Python will fail comparing items if priorities are equal without a consistent tiebreaker. Click onQ calls heap pq.heap push with a triple priority IDX item. O log n. The queue calls heapq.heap pop, which extracts the minimum triple. O log n. The demo inserts low with priority 3, urgent with priority 1, medium with priority 2. Despite the insertion order, the queue returns them in priority order, urgent, medium, low. Click a heap diagram shows why. Urgent at priority 1 sits at the root, the minimum is always at the top, accessible in O1 peak. Click the comparison table, heap queue versus assorted list. For heap queue, onQ and dequeue are both O log n, and peak is O1. For assorted list, insertions are On, but dequeue and peak are O1. The choice depends on your workload, but heap queue is almost always the right answer. Click the callout is critical. Python's heap queue is min heap only. To implement a max heap or a max priority queue, negate your priorities, push, priority item, and negate again when you pop. This is the standard Python idiom. Next, Python ships 3 thread-safe queue classes in the queue module: queue for FIFO, LIFO queue for LIFO, and priority queue for priority ordering. These use internal locks to make operations safe when multiple threads access the same queue simultaneously. Click Queue Usage. Put to in queue. By default, it blocks if the queue is full until space is available. Get to dequeue blocks if the queue is empty until something arrives. Put _now8 and get _now8 are non-blocking variants that raise exceptions immediately instead of blocking. LIFO queue is a thread-safe stack. Get returns the most recently put item. Priority queue is a thread-safe priority queue. Put tuples of priority item, and get always returns the minimum. Click the producer-consumer pattern is the canonical use case. A producer thread generates work items and puts them in the shared queue. A consumer thread takes items and processes them. The none sentinel signals the consumer to stop. The queue handles all the synchronization. The producer and consumer threads never need to know about each other, only about the shared queue. Click one important caveat. If you're writing single-threaded code, use collections.dequeue instead. The queue module's classes carry locking overhead on every put, and get unnecessary cost if there's no thread contention. Match the tool to the threading model. The DSA, pronounced DEC, is the most general linear container we've seen. It supports O1 push and pop at both ends. It's more capable than a stack or queue, because it generalizes both. Click Append Left and Pop Left operate on the front. Append and Pop operate on the rear. All 4 are O1. This is the key property. Python's collections.dequeue is implemented as a doubly linked list of fixed-size blocks, giving true O1 at both ends with good cache performance. Click the sliding window maximum problem showcases the monotonic dequeue pattern, one of the most powerful algorithmic tricks you'll encounter. We maintain a dequeue of indices where the values are in decreasing order. For each new element, evict from the rear any index whose value is smaller than the current element. It can never be the maximum of any future window. Evict from the front any index that has left the window. The front of the dequeue is always the index of the current window's maximum. Output 4, 1, 3, -1, -3, 5, 3, 6, 7, with window size 3, 3, 3, 5, 5, 6, 7. ON total, because each element is pushed and popped at most once. Click the diagram and table on the right, summarize the dequeue's role as a unified abstraction. A stack is just a dequeue where you only use the rear. A queue is a dequeue where you enqueue to the rear and dequeue from the front. The dequeue unifies both. Next, let's put the two structures side by side for a clean comparison. The stack has one active end, the top. You push and pop from the same place. It naturally models any process where the most recent thing must be handled first. Recursion, undo, bracket matching, DFS, expression evaluation. The queue has 2 active ends. Items enter at the rear and exit at the front. It models any process where fairness and ordering matter. BFS, OS scheduling, print queues, producer-consumer pipelines. Click the big complexity table at the bottom, brings in the dequeue and priority queue for a full comparison. Stack and queue operations are O1. Dequeue is also O1 at both ends. Priority queue is O log n for insert and remove, the cost of maintaining heap order, but O1 for peak. The order row captures the fundamental distinction: LIFO for stack, FIFO for queue, either end for dequeue, and priority-based for the priority queue. Pick the structure whose ordering model matches your problem's requirements, and everything else follows naturally. This is a classic interview problem you will almost certainly encounter. Implement a FIFO queue using only 2 stacks. The trick is clever, and the amortized analysis is important to understand. Click 2 stacks. Underscore inbox receives all new items. OnQueue always pushes to inbox, 01. Underscore outbox is the DQ side. Click OnQueue is trivial. Just push to inbox. Underscore transfer is the key method. When the outbox is empty and we need to DQ, we pour all of inbox into outbox by popping from inbox and pushing to outbox one by one. This reverses the order. So what was at the bottom of inbox ends up at the top of outbox, which is exactly the FIFO front element. Click DQ calls underscore transfer first. If outbox still has items from a previous transfer, we use those first and avoid unnecessary work. Then we pop from outbox. Click the diagram makes the reversal visual. Inbox has 30 at top, 20 in the middle, 10 at the bottom insertion order. After transferring to outbox, 10 is at the top, correct FIFO front. One pop from outbox gives us FIFO behavior. Click the amortized analysis. Each element is pushed to inbox once and popped from inbox once during transfer. Never more than that. The total cost of N operations is ON amortized 01 per operation. It feels like we're doing extra work during transfer, but each element gets transferred at most once across its entire lifetime. The reverse problem. Implement a LIFO stack using 2 queues. This approach has a different complexity trade-off. We pay ON on push and get 01 pop. Click push, enqueues the new item into Q2, then moves everything from Q1 into Q2. Then swaps the references. Q1 becomes the reordered queue. Q2 becomes the empty scratch space. The effect. After every push, Q1's front element is always the most recently pushed item. Dequeuing from Q1 gives us LIFO behavior. Click pop and peek. Just call Q1's dequeue and peek 01. Click the diagram confirms the Q1 state after pushing 10, 20, 30. The front of Q1 is 30, the most recently pushed item. Dequeue from Q1 returns 30, correct LIFO. Click the trade-off table summarizes both conversions. Q1 to 2 stacks, 01 on queue, 01 amortized dequeue. Stack via 2 queues, ON push, 01 pop. Interview insight. If you need frequent pops, stack via queues is fine. If you need frequent pushes, queue via stacks is better. Both demonstrate deep understanding of how these structures relate to each other. Next. The monotonic stack is a powerful pattern that shows up constantly in interview problems. Next greater element, largest rectangle in histogram, daily temperatures, trapping rainwater. The pattern is always the same, and once you see it, you'll recognize it everywhere. A monotonic stack maintains its elements in either strictly increasing or strictly decreasing order. We manage that invariant by popping before pushing whenever the new element violates the order. Click next underscore greater finds. For each element, the first element to its right that is larger. We scan left to right. For each index, while the stack is non-empty and the value at the stack's top index is less than the current value is the answer for that top index. Pop it, record the answer, and keep checking. Then push the current index. Any indices still on the stack at the end have no greater element to their right. They stay at -1. Click the trace for 4, 5, 2, 10, 8. Push index 0, value 4. At index 1, value 5 is greater than 4. Pop index 0, record result 0, equals 5. Push index 1. At index 2, value 2 is less than 5. Push index 2. At index 3, value 10 beats both 2 and 5. Pop index 2, record 10. Pop index 1, record 10. Push index 3. At index 4, value 8 is less than 10. Push index 4. Remaining indices 3 and 4 stay at -1. Final result, 5, 10, 10, -1, -1. 1 pass, ON total. Each element is pushed and popped, at most once. Complexity summary, your reference card. For stacks, push, pop, peek, and size are all 01 for both the list-based and linked list implementations. The minor difference is that list-based push is 01 amortized, occasionally triggering a resize, while linked list is 01, exactly. Space is ON for both, but the linked list version has pointer overhead per node. For queues, the DSA implementation and the linked list implementation both give you 01 for all operations including dequeue. The list implementation is 01 for onQueue, but ON for dequeue. That's the disqualifying row. If you use list as a queue, your BFS becomes ON squared, and your interviewer notices. Click for priority queues. Heap queue gives O log n for onQueue and dequeue, but 01 for peak minimum. Building a heap from n elements is ON, not ON log n, because of the Floyd heapification algorithm. A sorted list inverts the trade-off. ON, insert, 01, remove from the end. Click the callout is the single most important thing on this slide. List.pop, 0 as a dequeue, is ON. This mistake alone turns correct BFS code into an accidentally quadratic algorithm. It's subtle because the code looks correct and runs correctly, just slowly. Use stickWay. That's the rule. Next, let's lock in the common mistakes and their fixes. Click Pitfall 1, using a plain list as a queue. Q.pop 0 shifts every element ON. We've said it twice now, it bears repeating. Pitfall 2, not checking for an empty stack before popping. This raises index error and crashes your program. Always guard your pops. Pitfall 3, using Q.queue in single-threaded code. The thread-safe queue acquires a lock on every put and get unnecessary overhead when there's no concurrency. Single-threaded code should use collections.dque. Pitfall 4, expecting a max heap from heap queue. Python's heap queue is min only. heapq.heappop returns the smallest element. If you push 5 and 1 and call pop expecting 5, you get 1. Negating priorities is the standard fix. Click Best Practices. DSA for queues, plain list for stacks, append and pop at the tail are O1. Heap queue tuples with priority item for priority queues and negate the priority for max heap. Always check empty before popping or peaking. And use if stack instead of if len stack equals 0. More Pythonic and slightly faster. Let's bring it all together. Click Stack. LIFO. The quickest Python stack is a plain list. Append to push, pop to pop, -1 to peak, not s to check empty. All O1. Applications. Function call stack. Undo/redo. Balance bracket checking. Postfix evaluation. DFS. Monotonic stack patterns. Click Q. FIFO. Always use collections.dque. Append to enqueue at the rear. Pop left to dequeue from the front. Q0 to peak, not Q to check empty. All O1. Applications. BFS. OS scheduling. Print queues. Sliding window maximums. Producer consumer. Click priority queue. Use heap queue with tuples of priority item. Heap push is O log n. Heap pop is O log n. H0 for O1. Peak. For a max heap, negate the priority. Applications. Dijkstra's algorithm. A star. Task scheduling. Any problem with always process the highest priority item next. Click the two diagrams. Summarize the structural difference visually. Stacks have one active end. Queues have two active ends with distinct roles. Keeping that picture in your head is all you need to know which structure a problem calls for. Screenshot this slide, write it on paper, paste it somewhere visible. Stacks and queues show up in every part of algorithms and system design. These patterns are foundational. Next. And that's a wrap on stacks and queues. We went from the LIFO and FIFO definitions all the way through list-based and linked list implementations, circular queues, priority queues, the queue module, DAKes, the classic interview problems, queue from two stacks, stack from two queues, and the monotonic stack pattern. If this was helpful, hit the like button and subscribe so you never miss a video in this Python DSA series. Drop any questions in the comments and I'll get back to you. See you in the next one.